Welcome to the talk Synthesizing Computable Functions from Rational Specifications over Infinite Words. What is synthesis? In synthesis, the goal is given a specification to synthesize, that means automatically generate, if possible, an implementation. A specification is simply a relation between inputs and outputs, and an implementation is a function from inputs to outputs that has the same domain as the specification, and for each pair of input and selected output by the function, this pair is in the specification. Here's a simple example of a specification given in LTL. It describes a traffic light. A traffic light is green infinitely often. Then once the traffic light is red, the light cannot become green immediately. And once red, the light always becomes green eventually after being yellow for some time. This can also be described in LTL, but I left it out for this example. On the right-hand side, we see a program which satisfies the specification. First, when the light is green, then after 120 seconds, the light goes to red. Then the red period is 30 seconds. After that, the light goes to yellow, and after 5 seconds, the light goes to green again, and again we have a green phase of 120 seconds, and so on. While this is probably not the safest traffic light, it satisfies the specification on the left. Program synthesis is undecidable in general. It depends on the classes of specifications and implementations one considers if program synthesis is decidable. For example, for LTL specifications, such as I have given here, synthesis is decidable, but if we take more complicated specifications, for example, first over logic over more complicated input types such as arrays, synthesis becomes undecidable. So what's the goal in this talk? Our goal is to synthesize stream processing programs from binary relations of infinite words. So specifications that are not as complicated as arrays or something like that, just over words. Okay, here are some examples. Here we have a specification. The input string starts with a finite segment over the letters A and B. Then we see some special symbol x, which is either a big A or a big B, and then the remainder is an infinite string composed of A's and B's. And outputs that can be combined to these kind of inputs start with the same special letter that was seen in the input word. Then we have the same prefix that was seen before in the input word, and then we have some reminder, which is any infinite string over A and B. So this kind of specification can be implemented by a program. What does the program have to do to implement it? A program processes the input stream, and it reads and stores the input until our special symbol, either A or B, occurs. Then it can produce A or B and the input that was stored before, and from then on it can simply copy the remainder of the input letter by letter. Here's another specification which is even functional. The input is a bit stream and the output is also a bit stream, and every bit is flipped. And of course, there's a program that can satisfy the specification. It simply reads the input letter by letter and produces for every input bit 0 a 1, and for every 1 a 0, and this can be done in a reactive way. Read one input bit, produce one output bit. Let's now be a bit more formal. What do we mean by stream processing programs? We mean computable functions in a Turing computable sense. So what does it mean? We consider partial functions from infinite words to infinite words, and we say such a function is computable if there exists a deterministic Turing machine that looks as follows. We have 3 tapes. We have a read-only one-way input tape that can be read from left to right. We have a working tape, which is bidirectional. It can be read and written on. And we have an output tape, which is write-only from left to right. Okay, and when the input tape holds some input word from the domain of the function, then the following must be satisfied. Whenever the machine reads longer and longer prefixes of the input word, then the output tape should contain longer and longer prefixes of the value the function maps the input to. And it is important that we talk about partial functions. It means that whenever the input tape holds some word which is not from the domain of the function, we do not care what happens in the computation of the machine. So let's take a look at some examples so we understand the notion a bit better. Here we have this function which was chosen as the implementation of the specification from 2 slides ago. So inputs of the form u, where u is a finite prefix of over a and b, and the special symbol big A, and the remainder of a's and b's is mapped to a, then the prefix, and then also the remainder. And if in the middle we have a b, then the output starts with this special letter b, then we have the prefix before and the same remainder. So we have already seen that it is computable. Surely a deterministic Turing machine can use the working tape to store the remainder, the prefix which comes before the special letter a and b, then go back on the working tape to produce the desired output. Another function, we have an infinite input word over a and b, and the output should be a to the omega if the input word contains infinitely many a, and otherwise the output should be b to the omega. This function is not Turing computable by a deterministic Turing machine, because in order to start with the output, it would have to know whether the input contains infinitely many a or not, which is something which cannot be known. And since the output tape cannot be erased, it is not possible to correctly start with the output sequence. Okay, so let's be a bit more specific about what kind of relations over infinite words we consider. We consider omega rational relations. What are omega rational relations? These are relations from infinite words to infinite words that are recognizable by non-deterministic parity transducers. What are parity transducers? In transducers, the transitions are labeled by pairs of words. The first word is the input word, and the second word is the output word. And the acceptance condition is parity. For example, here, this automaton here first distinguishes after the first output symbol, which is big A or big B. Then it simply copies the input. And then here it expects in the input an A. Produces nothing. Goes to this state here, and here every input can be combined with every output. Or if we go this way, if the first output symbol is a B, then we expect a B in the input here. So in this relation, this transducer recognizes the relation, which was the specification I have shown you two slides before, this one. Okay, here's another automaton. It only has one accepting state, and in the output it can be non-deterministically chosen to replace an A in the input with two A's. Okay, so we consider omega rational specifications and want to decide whether we can synthesize a computable functions from it. Unfortunately, this is an undecidable problem. And the proof is an easy adaptation from the finite word setting. There it was shown that it is undecidable whether a sequential function can be synthesized from a rational relation. Even though we have this negative result, we have also a positive result. We have a game reduction. So if an omega rational relation is given by a transducer T, then from T we can build a game which has an omega regular winning condition, and whenever Eve has a winning strategy in this game, then it is possible to synthesize a computable function from the relation. Okay, so I want to go into a bit more detail. How does this game look? It's a two-player game. The player Adam provides an input word alpha letter by letter, and Eve does not provide output, but she must build a run of the transducer on the input word. And she is able to skip her move, because as we have seen, the output might depend on future inputs. For example, in the specification shown you, we have to wait for the special symbol big A, B in order to know what the right move is. So in this game, she has the ability to skip her move before she continues building the run. And this is a problem, as we have seen in the example. It might be arbitrarily long until it is known for Eve what kind of move she must make. So the look ahead needed can be arbitrarily long, and our goal is to build a finite state game arena. So yeah, to solve this, the look ahead is not stored explicitly but abstractly. Okay, then for the winning condition, the relation can have a partial domain, and the computable function we want to synthesize should have the same domain as the given relation. So for the game, we only care what Eve does whenever Adam spells a word which is part of the specification domain. And if Adam spells a word which is part of the specification domain, then it is Eve's goal to build an infinite accepting run of the transducer on this given input word. And this means that Eve cannot use her skip move indefinitely. She must continue building the run from time to time. And this captures the property that the function we obtain is computable. Okay, so we have seen that it is undecidable whether we can synthesize a computable function from an omega rational relation. And we have seen the game reduction. If we can find a winning strategy in the game, then we can synthesize a computable function. But of course, since we have this undecidability result, this reduction is not complete. So let's take a look at an example where the game reduction fails. Here we have a simple transducer. The domain of this function is either an input string a to the omega, and the output is also a to the omega, and this can be recognized in two ways in this transducer. For example, one could go the upper pass and accept the infinite a string here, or one could go the lower pass and accept the infinite a string here. Then it is also possible that there either once in the input occurs an A or a B, and for the A the upper pass has to be taken, for the B the lower pass, and the output is always the identity. Of course, this relation is of course functional, and thus it is clearly that this is a computable function. But if has no winning strategy if we build the game corresponding to this transducer. Why? Because since a to the omega is a valid input in the domain of the relation, if Adam plays a again and again, at some point Eve must make an output move and start building a run in the transducer, because otherwise she would not provide an infinite run, which would mean that the run is not accepting because it's finite, but the input is a word from the domain, so she would not win the game. So at some point, when Adam continues to play A's, she must start to build her run, and she either has to decide to go into this part in the automaton or this part in the automaton, and depending on her choice, then Adam can either provide this special letter A or B, such that Eve cannot continue to build the run in the part of the automaton she has chosen. So she will lose the game, but of course the function is simply the identity function, so which is computable. So she lost, even though we can synthesize a computable function from this transducer. But we can make the game reduction complete. We have a structural property P on a transducer. The property is rather technical, so I won't define it. The main point of this structural property is that when we have a pair of input-outputs, then the state that is reachable by this input-output pair is uniquely determined. So that's the main point of this property. While this property may sound a bit artificial, it is a property that naturally holds for known classes of rational relations. It holds for omega automatic relations. These are the relations that are captured by synchronous transducers, and these kind of relations are also used in church synthesis, which I will come back to later. And an even bigger class, which contains the omega automatic relations, are the omega deterministic rational relations, which I'm not going to define. Okay, and so whenever we have a transducer that satisfies this property, then the game reduction is complete, so it is decidable whether a computable function can be synthesized from such a transducer, and this problem is X-time complete. Okay, now let's see what is the relation to church synthesis. In church synthesis, the specification is given by an omega automatic specification, so a synchronous transducer, which means letter-to-letter transducer, and the implementation should be done by a very simple device, a mini machine which is simply a deterministic machine that alternates between reading an input symbol and producing an output symbol. Okay, so then church synthesis is decidable, so we can algorithmically decide if there exists such a specification, and if yes, this is good, but if no, now we don't have to stop, even though the specification might not be implementable by such a simple machine as a Mealy machine. We can ask, is it implementable by some computable function? And this is then also decidable. Here is the specification where we have to wait for our special symbol A or B, and can then produce the output starting with either A or B. We have seen that this function, that the specification is implementable, but this cannot be implemented by a Mealy machine because input and output have to alternate, and after reading the first input symbol, it is unknown what must be the first output symbol, because our symbol, a big A or B, might occur arbitrarily far in the input. If we take the other specification from the very beginning, which was functional, where we simply have a bit stream and the output should be the bit stream with the flipped bits, then this can be implemented by a Mealy machine. For every 0, the output is 1. For every 1, the output is 0. Okay, so we have seen we can decide for certain classes of omega rational relations whether we can synthesize a computable function, which we defined as computable by a deterministic Turing machine. But is it necessary to use the whole computing power of Turing machines? And it turns out that it is not necessary. It suffices to consider deterministic two-way transducers. So whenever we have that Eve has a winning strategy in the constructed game, then the synthesized computable function can also be implemented by a deterministic two-way transducer, which is of course very nice because deterministic two-way transducers enjoy a much more nicer algorithmic properties. For example, equivalence is decidable. Okay, so let's take a look at an example of our specification where we wait for the special symbol, and this was some possible implementation, which is a computable function. How can this be computed by a deterministic two-way transducer? Here, if this is the input stream, a deterministic two-way transducer has one output tape, and it can read the input going left and right. So the transducer starts reading the input, it simply goes right, produces no output. Eventually we see our special symbol, either A or B. Here it's A in this case. Then we can change the direction, go back to the beginning of the word, still produce nothing, and then when we've reached the beginning of the word, we can produce the special letter. We have seen A in this case, and then simply copy the input string. So A, B, A, and so on. And from here we simply copy the seen letter. Okay, so if we again take a look at the specification, why is it that we have to go back in the input and cannot directly have to read in the, like here, that we have to read fine to the input and then know that we have what we have to produce? Why is that? It is because this domain is partial. Here the domain, the special symbol occurs exactly once, and we have to wait for it in order to know what the output should be. So let's think about what happens if we try to make the domain total and see if it remains that we can still implement the specification. So in order to make the domain total, every word that contains either none of the special symbols or more than one of the special symbol, it must be added to the domain. And in order to keep the specification the most general, let's say every of these inputs can be combined with any output. It turns out that then the specification is no longer implementable. Why? Because let's say we have a string beginning just with A's. In order to be computable at some point, it must be known how the output should begin. If a deterministic machine chooses the output should begin with a special letter, for example A, then for the input we can simply continue the input with the other special letter which was not chosen at the first input letter, and then it is no longer possible to complete the output word such that this input-output combination is part of the specification. Another option is that if input starts to build a word starting with a sequence of A's, that the deterministic Turing machine would at some point produce an output letter small a or b, and in this case, if then in the input there occurs exactly one of the special letters, then the output should have started with the special letter, and it's also not possible to complete this output such that this input-output combination is part of the specification. And it turns out that whether or not a domain is total has an influence on the difficulty of the implementations. So if we have given a specification by a transducer that satisfies our property, then we can decide whether there is an implementation by a computable function. And well, if no, there is nothing that can be done. But if yes, we can distinguish whether the domain of the specification is total or not. And if it's not total, if we have a partial function, then we know that in order to implement this function, we can use a deterministic two-way transducer. And if the domain is total, then it turns out it is only necessary to use one-way transducers. And the main difference between one and two-way transducers is that one-way transducers are finite memory devices, while two-way transducers, well, they have a finite state space, but they need arbitrarily long access to the input stream. So the input must be stored in some way to be still accessible for the two-way transducer. Another thing is that this not only holds for domains which are total, but even for any domain which is closed, and it is decidable whether a domain of a omega rational relation is closed. Okay, that's it. Let me come to the summary. We have seen it is undecidable whether computable functions can be synthesized from omega rational relations. We have an incomplete but sound reduction to an omega regular game, which means a game with an omega regular winning condition. But the reduction becomes complete for large subclasses of omega rational relations, for example, omega automatic relations. And if such a computable function can be synthesized, then it can be implemented by a deterministic two-way transducer. We don't need to use the whole power of Turing machines. And furthermore, if the specification has total domain, then even one-way transducers suffice.